80 times 10 to the 6th pascals. And the diameter of each bolt is 6 millimeters, or 6 times 10 to the negative 3 meters. Yeah. Yeah, for going back a couple slides here. For normal stress, sigma was how we designate normal stress. For shear stress, we use tau. That's right. So tau max, 80 times 10 to the 6th pascals. In this case, we're not necessarily completely told this, but we're going to assume that P is acting in the center since we don't really have those dimensions. So we're going to, this will come into play when we draw our free body diagram. P is going to act at the center in between those bolts. And what we're looking for is the maximum value of that applied force P before our bolts are going to fail due to the shear stress exceeding 80 megapascals. Any questions on what we're trying to find here? In order to find shear stress, we need to know internal shear force in our bolts. So we're going to need to have a free body diagram to do this. The free body diagrams now for internal loads are not necessarily as simple as we were seeing before. We have to see how can we cut through this where it's going to expose the things we're interested in without including things that we're maybe not interested in or don't need to find. So to find the shear stress in the bolts, we need to know the shear force in the bolts, meaning that we're going to need to cut through them in a plane that's parallel to the top of this beam here so that we can expose those. So the way we can do this is I can actually, unlike what we've really seen before, I can make a cut through these bolts right above the top part of this wood, and I can also cut through the bolts below this bottom piece of the wood here. And what I'm going to do is by cutting through those bolts, I'm going to be exposing what those shear forces are. So in my attempt of a 3D picture, I'm including the piece of wood here. I'm going to make a cut through both bolts I'm just isolating this top piece of wood that we have. So if I cut through the bolts, what do I have to include in the free body diagram? Right. In general, just like we saw in the quiz, whenever you cut through a solid piece, you would be exposing internal normal force, shear force, and bending moment. For these problems, we're only looking at shear stress. I'm going to just simplify it and just be looking at their internal shear forces. There could potentially be normal forces and bending moments there. We're not analyzing normal stresses in this example, so I'm not going to be drawing those. So for the simplification, since we're only looking at shear stress, I'm only going to draw the shear force. In general, and we'll visit this towards the end of the semester, we can have all of the P, the V, and the M non-zero, and all these different stresses acting simultaneously. For right now, we're not going to worry about that, though. All right, so at the top, because of symmetry, I'm going to assume that the shear forces are the same in the two bolts. This would be different if P were not centered between the bolts, then they could possibly be different. For simplicity here, I'm assuming everything's in the center, so they're going to be equal. So I cut through the top here, and I only drew the two internal shear forces. I ignored for the moment the bending forces, the bending moment, and the normal force. But I'm also making a cut at the bottom of the piece of wood through the other side of the bolts. So I also need to include, because I cut through a second surface, there's also a shear force on that bottom surface. again, because of symmetry, I'm going to assume it's the same value V in all the places. So because I cut through really four surfaces here, each one with that internal normal force, all four of these surfaces are resisting this applied load P that I'm applying at the end of this piece of wood here. So there's 4 internal normal forces, and there's 1 applied force here. So if you trust me that this is the free body diagram here, we only have forces acting in what I designated the x direction. So we can figure out that if we sum forces in the x, we're in equilibrium, it's going to be 0. We'll have 4v minus p. Therefore, on each surface of the cut bolts, the internal shear force is going to be 1/4 of our applied load P. And we're going to need to know the internal shear force so that we can calculate the shear stress on the bolts. We're told that the maximum shear stress that each bolt can withstand is 80 times 10 to the 6th pascals, or 80 megapascals. And for this section, we're just talking about average shear stress. So our calculation for what the shear stress is just V over A. We just found the internal shear force on each surface of the bolt was P over 4. How are we going to calculate the area that this internal shear force is acting on?
Cross-sectional area of the bolt.
Right, it's the cross-sectional area, and this is where we have to be cautious because there are different ways we could represent this, like we saw last Thursday. The way that I drew this, I put for each face or each surface its own internal shear force V, meaning that this V is only acting on this cross-sectional area. This V is only acting on this cross-sectional area. Another way I could have represented this is made all 4 of those cuts and said there's one collective V acting on it, but then the surface area will be all 4 added together. In this case, the V is only acting on the surface area from one bolt, which we're told that we can calculate that, but it's just this single surface area here. So the surface area that's acting on, we're going to use pi d squared over 4, or if you prefer using radii, pi r squared. But we're told the diameter here, so I'll stick with that. So the area is going to be pi times 6 times 10 to the negative 3rd squared over 4. From this equation, we know that P over this is going to be equal to 80 times 10 to the 6th pascals. So the only unknown we have in this equation is what that applied load is going to be to cause the shear stress in the bolt to be 80 megapascals. And we find that if the applied load is 9.05, or about 9 kilonewtons,